So I'm going to try and fit this in 25 minutes. And this is basically the story of what we've been doing in the space of robotics and agriculture. And primarily, I just want to talk a little bit about some of the motivations, what we've been able to accomplish and where we would like to go. So this is my first time talking at MobiSys. I typically go to RSS and ICRA and all the robotics, and sometimes I go to NeurIPS and the AI conferences. But I really enjoyed seeing the banner on at least this workshop, and it was like the location is Mars Solar System Milky Way. So that was pretty cool, and it's also quite resonated with us because at EarthSense, which is the company that I co-founded, 3 weeks ago we won the Type 50 award. And there, the first slide that the CEO splashed was this one. It was Mars, and he made the claim that EarthSense is working towards technologies that will terraform Mars eventually. But there's a lot of opportunity to heal the planet, so we're starting on Earth. So jokes apart, what I'd like to talk about is robotics for really impacting large-scale landscapes in a meaningful way. So my group works in robotics. We're at the University of Villanova-Champaign. You heard the long list of affiliations that we have. And primarily, we are a number of students from different departments: computer science, electrical engineering, mechanical, ag, aero, all kinds of things. And we kind of work on this autonomy triad. And we call ourselves a full stack roboticist. So in the sense that we work on all three aspects of the robotic system and then actually the system itself. More recently, some of the mechanical work has been pushed out of my group into the company because it's just much easier that way. We're not really well equipped to do large-scale manufacturing. But we do work quite a bit on perception, planning, and control. And the key thing that we think is important about robotics and AI is that all of robotics AI has to be at the edge. And not only it just has to do inference, but it also has to learn at the edge. So this is a classic example, right? So here's an airplane that's flying happily, and then suddenly half of its wing drops off. Now, this is not something it has encountered in its previous experiences. So how does this airplane adapt to this very sudden change? Now, humans are able to do this quite well. So our big dream is if we can get robots to do the same thing in real time at the edge and on resource-constrained hardware. So edge AI to the extreme is one way to look at this. So in this particular case, it actually does work. And it's quite a bit of it is rule-based. This is back in the day, 2013, when I used to work a lot more on airplanes. And here there's a number of rules in there, behaviors in there, and those behaviors kind of compete against each other to keep the airplane in flight. So it's trying to fly faster to account for the loss in lift. It's trying to, as it tries to turn, the two behaviors of trying to keep the altitude and maintaining turn rate are fighting against each other. So it's been heuristically designed. And so our journey for the past many years has really been to try and remove more and more of those assumptions and come towards a computing system that's capable of learning at the edge in real time. And what we've done in the past 3-4 years is we've found a very meaningful application to bring these types of technologies to bear, because the real world is messy and that's where you need adaptation. So agriculture is a really good place where these technologies can be useful. And what I'm going to do most of this talk today is talk about what some of those applications could be. So today, this is a diagram from Foley's 2011 paper, Nature paper, about how could we feed a growing population. And this is where we are today. So this flower diagram shows that we're able to feed our current population, more or less, but the cost of that in terms of the environmental impact is just tremendous. And what we'd like to do is bring this flower into balance. And if we can do that, then we can not only feed our population, but be sustainable. So how do we do this? So one of these dreams that we have is that we can decentralize a tractor. We can have a lot of smaller, much lower cost equipment be operating in fields, little robots that can scale from small farms to large farms and are enabled by AI and connectivity at the edge. And we think that these types of systems will enable new types of management techniques in agriculture that are currently not possible such as under canopy phenotyping, mechanical weeding, spot side dressing, which is spraying nitrogen on the side, and cover crop planting. So I'll talk a little bit about these things. So the first thing to understand about agriculture is that it's a humongous industry, and it all starts at the seed. So the product design, like what seed you sow, that's what you reap. So there's a huge industry in making better seeds. After that, the seed goes into farms. In order to be more sustainable in the farms, we have to reduce the amount of chemicals we're using there. Eventually, we'd like to move more towards diversified integrative agriculture. Right now, I'm sitting in Illinois, but I'm eating strawberries that come all the way from California, and they're very delicious, but they have to travel 3,000 miles before they get to me. So, and then the soybean that we grow here is fed to pigs in China. So it's really modularized and disjoint, and that's very difficult to manage. And so eventually we'd like to create AI that can deal with entire ecosystem level agricultural systems rather than the monocultures that we have today. So starting with seed is a good place to begin because that's where there's a huge potential for impact. So corn or maize, which is a very popular crop in the Midwest, about 400 million acres is rotated across corn and soybean in the Midwest. It's the largest grown crop in the world. Is actually not a natural crop. So it started like 9,000 years ago, Native Americans in South America started with this plant, which looks nothing like corn. It's like a grass. And then they selectively bred it towards corn. And 3,000 years ago, we see the modern varieties of corn. And right now, some of those varieties are stored under the North Pole. So in case we get hit by a meteorite, we don't have to go 3,000 years back. And this is the same story for most of the vegetables and plants and even animals that we work with in agriculture. They've been selectively bred. So the question is, how can we accelerate the pace of this breeding so that we can feed people in Africa where the population is going to double, but the productivity is 3 times less? In order to do this, the large seed companies and scientists solve what's known as a GWAS problem. So they've sequenced all the genes, they can measure the environment, and if they can correlate the genotypes to phenotypes, which is their expressions. So for plants, it'd be height. For corn, it could be stem width, it could be the height of the ear of corn, it could be yield, it could be disease resistance. If they could map this with machine learning or something, then they can selectively breed in a much more focused way rather than the trial and error way that they're forced into right now. So to do this, they actually run these massive experiments, right? What you may call as reinforcement learning experiments in some way, where over about 10 million plots, I think, every year are planted across the United States, where each of these plots is a 3 by 3 meter piece of land. And in that, they plant a different variety and they try to compare the performance of these varieties against each other under different environmental conditions or chemicals. And what they need to do is kind of pinpoint which one of these are doing really well, measure the phenotypes. And all of these phenotypes are today measured by hand. So you have this person counting, these two measuring height, this one is measuring stem width. This is obviously expensive, time consuming, not very accurate. So we need to automate this. So we can automate it with gantries or airplanes, but gantries are expensive. Airplanes don't really get the data under the canopy. So what we need are robots. And this is not new, right? People have been talking about ag robots for like a long time. But if you look at where we are, we really don't see any ag robots out there, and we really don't even see that it's in the, it's on everybody's mind. And that's primarily because it's a very difficult problem. So it's all boils down to really cost. But the easy part of the cost is how do you make a cheap robot? The more harder part of the cost is how do you make that robot autonomous? Because if you have to have a person or 6 people babysitting a robot in this case, then that's not scalable. So this autonomy problem is really difficult because the scales in ag are really vast, the data sets are not very nice, and the environment can have lots of surprises. So what we started working on about 3 years ago now, 2018, 2017, is this idea of really small, low-cost, autonomous robots that could go under the canopy and get data that is not visible to drones and satellites. And with this, we were hoping we could make a delta difference in phenotyping, and that would be a difference in seed making, and that would impact the US market, of course, but also more emerging markets like Africa and India. Now, this actually won a Best Paper Award in RSS 2018. And one of the cool things about the system that we had created, this small system, was that it kind of simplified the problem quite a bit. So a lot of people were working with these larger robots. So here is an example that we had, but these were quite bulky, very heavy, difficult to move, created a lot of logistics problems. And here you see it kind of kills that plant right there. So it sucks it down in the tracks and just kind of kills it. So one of our ideas was, how can we simplify this? And this came from my drones background. And we were thinking, well, really make a very simple robot. It's 3D printed, and it has like these sensors on it, and it can go through. And then farmers really liked the idea, and then it took off. So from then in 2018, we made 30 of these robots. We had this company co-founded, EarthSense, which would actually do the engineering work of making the robots. In 2019, and the first time we made them, they broke all the time because field conditions are pretty difficult. 2019, they kind of figured out how to make them really nicely. And 2020 and 2021 now, they've really upgraded and made these into polished products that are really rugged systems on wheels. So here's an example of these robots, right? So they have brushless DC motors, 4 cameras on them, LiDAR in the front, LiDAR in the back. There's a GPS receiver on them. There's an Intel NUC computer in there, and we'll talk about why the NUC and why not the NUC. And then there's IMU and a bunch of other internal sensors on them. So here you see that this thing, it's pretty tough. It can deal with quite a bit of different types of environment. And here's an example. And so in 2021 now, what they've done is they've upgraded the motors to something really powerful. And this has been a very interesting learning experience for me personally, in terms of like designing these really low cost and ruggedized systems. So we never thought that we'd make a robot that would be this strong, but it looks like we can. And a lot of things are coming together, compact computing for sure, modems and communication, but also brushless DC motors, which have been pushed forward by all this electric scooters trend. So this one has 4 of those brushless DC motors, and you can see that it has enough power to pull like a tractor, which is quite heavy. So these things can get really powerful. And so now the question is, we made these robots, how do we kind of make them autonomous? So we started in 2018 with GPS, which is kind of what you go to when you want to do outdoor autonomy. But very quickly found out that even though we can get like the basic performance done really well and and write papers about them, the issue is that when you start going under the plant canopy, this GPS starts to lose accuracy. So when you're outside, everything's great, this works great. But when you go under the plant canopy, it starts to lose accuracy. So we have to do this reactive sensing and what we call the row following behavior. So you have to detect these rows of crop, and then you have to estimate the distance to the row and the angle so that you can kind of stay in between that row as you're driving. The challenge is the data that you get from those LiDARs. Again, remember, we're trying to keep the costs low. And in either case, LiDAR is always going to give you some kind of a point cloud. So here, the LiDAR is in the middle, and it's scanning the rows. And these points are range measurements. And you can see that it's quite a mess. And from that mess, we have to kind of guess where those rows are. So this is a pretty hard problem. And so we spent quite a bit of time figuring this out, and it seems to be working now fairly well, to a point where I could go in my favorite hobby, which is kicking the robots, and try to make sure that they're working. So that was kind of our first big success, is that we can get these things to be autonomous with LiDAR, which are slightly more expensive sensors, about $1,000, $1,500, but more easier to deal with in terms of edge AI because you're getting more limited data. So here, this was kind of one of the foundational technologies at EarthSense. So what EarthSense does is that it goes through, these robots of EarthSense go under the plant canopy for large breeding firms. They collect a bunch of phenotypic data from all the sensors. And then EarthSense has cloud AI algorithms like this one. And they live on the Microsoft Azure cloud, where they do things like estimating stem width, estimating ear height. So all the things that the human would have done, just like 100 times faster. So counting the number of plants and 100 times more reliable, in the sense that every time you run the robot through, you get a much more predictable result. Whereas with humans, it's hard to kind of measure the height of a plant, right? It's difficult to know where exactly you're going to measure. And then they deliver that data on a plot by plot basis to the user, and then the user can look at the field and go, okay, well, these varieties are doing better than the others. So that's kind of, I think the first success story that we've seen in this space of bringing robotics into the field. So we have 90 robots now deployed across the US, and some in Brazil and some in India. And we're growing pretty rapidly with that. So now the bigger story from academic and overall is, how do we take this technology from, remember the pyramid, from the seeds to the farm. So in the farm, if you come to the Midwest right now, you'll see basically something like this. So humongous tractors. So this tractor is trying to optimize this time of that one farmer by spraying at the same time some 30 rows of corn with chemicals. So basically replacing human labor with chemicals. This is, not sustainable. And this was known right from the times of 80s, for example, when herbicide-resistant cultivars were released and people started what we now call the spray and pray method of agriculture. So you just go out there, spray the crap out of your fields, and hope that nothing bad happens. And of course, the weeds don't grow, but what that has led to is these super weeds that are not killed by any of these herbicides. And they're proliferating pretty much everywhere across the world where we have modern agriculture. And this is just like one of the problems. We have hypoxia in the oceans. There's like pesticides in your beer, people not being paid that well. So if you go to India, you'll see that people are paid basically nothing, like 100 rupees a day, to manually weed the fields, because the farms are small and they can't really afford the big tractors. So the only way you could be profitable today is by growing big. And this is like, even in the US, if you look at the trends, it looks like farmers are keeping less and less of the money that they used to make. And even though labor costs have dropped because of equipment, they've been replaced and surpassed by the cost of intermediate goods, which is basically like chemicals, and the cost of capital equipment, with not land, so just the tractors. And in fact, the goods are now overpowering the tractors. And land, surprisingly, has stayed pretty flat or even declining a little bit. So it seems like this type of agriculture is pretty obviously very input intensive. So I believe, and many of us believe, that automating current equipment is not going to solve our problems, because we're just going to do more of the things that aren't working today. What we really need to do from an agronomic perspective is add more diversity, be more scale neutral in the way we farm. And eventually, we'd love to go back to the Amazonian rainforest, the edible forest that the Amazonians used to have, or the oasis gardens in the desert, which are extremely space effective in terms of their productivity. To get there, we need different equipment. So let me give you one concrete case study here. So in the Midwest, which is 400 million acres of arable agricultural land, 95% of that land is left bare for 8 months of that year, because you grow from April to September, or sorry, May to September. And then after that, it just stays there. So if you drive down in the Midwest, you'll just see like this corn and soybean desert. And this land, it could be sequestering carbon. And it's strange that agriculture inputs carbon 10% into the environment rather than sucking it in, which is what it should be doing, because it's, it's green stuff. So one way to change that is cover crops. Cover crops are basically little like grass type plants that you can plant in standing corn, and they grow before the corn is harvested. And then after the corn is harvested, you get these green fields. And then part of fall and spring, there's enough sunlight to kind of keep them alive. And then they can be used for a number of things, but most importantly, they sequester carbon and they replenish the land. But people can't do that today, because by the time they harvest the corn, it's too late. There's not enough sunlight. And during the season, if they air spray, then it's really low likelihood that it might come up. So one of these ideas that we have right now is robots that can go under the corn canopy, just like the older ones that we saw, but this time with a little hopper and an auger, and they could distribute these cover crop seeds in July and August, so much earlier than what you can do today after the harvest. And that would lead to a much more resilient cover crop stand. And because these robots are so cheap, maybe made at $500, $300 a pop, we could bring the cost down from $20 or $15 to like $5 or $3 an acre. And this cost is very important overall, like I've said. But to get here, we need to kind of bring the level of autonomy up to this level, level 3. So right now, we're maybe around here, right? 1 or 2. And tractors have lots of GPS systems, so they're around here, but you still need to sit in the tractor, hands off, but not eyes off. We're getting close to here, like you can take your eyes off the robot, but really in order to do things like cover crops or mechanical weeding, you need to have one person be able to control many robots and ideally not even be on site. But the trick is going to increase that level of autonomy and decrease that cost of autonomy. So cheaper sensors, cheaper computers, but still better AI. So right now, for example, we're using something like a NUC and a Raspberry Pi. So the question is, how can we, keep making that cheaper? The typical task is you have like these waypoints at the beginning and end of the row. Within the row, you can do the row following behavior. Then when you're outside, you can then switch to your path following behavior, then find the next one and then go back in. So here's an example of something like that. So first, you have this robot that's doing the row following behavior, and then it has a AI on it that's kind of figuring out when it needs to switch. So now it decides to switch. So it switches, then it turns around. This is now it's using the GPS to make that turn, GPS and inertial sensors. Then it has a waypoint in that next row. So it's like, okay, I'm going to enter that row, and it starts to get closer to it. And then it switches back to a row entry and a row follow behavior, and then goes in. And now this has to happen like, that's just one row, right? There's like 3,000 rows of these in every field. It has to happen reliably over and over and over and over again. And it doesn't always happen reliably. Like, so this is an example where there's a lot of mud caking on the wheels. So this causes the robot to kind of make some mistakes. But there's like adaptive controllers on there, which are trying to deal with this loss of traction. So they do that, and then the robot is going to try and turn in here again. But because of this, and because maybe there's mud also on the LiDAR, it basically makes a mistake. And it's going to hit that corn right there. But there's AI on it that detects, oh, something's gone wrong, backs the robot off, and then tries again. And this is pretty cool. Like, this is something that you can do with these little robots. You can't do this with like big tractors. If you make a mistake, you make a mistake. The consequences are quite high. But overall, we recently found that the LiDAR is good, but we need to go beyond. So we've been focusing on vision for navigation. And again, I don't want to go through the detail, but you can read the paper at RSS 2021. This is work jointly done with Saurav Gupta. And here what we're seeing is you have like this 240 by 320 image on the robot, goes through a deep learning network, and does the same thing that our LiDAR system was doing, but with this monocular image. It's detecting the angle to the row and the distance to the row. And then after that, it goes through the internal robot. I won't explain what these are, but there's like a filter to remove noise and fuse sensors. And then there's like a optimized path planner that's creating a good path. So all of this has to happen on board the robot. Of course, in order to train this, you need lots of data. And we kind of have gotten that. But it looks like at least visual navigation on robots seems like a real thing now with the work that we've done. This is happening on the NUC, Intel NUC on the robot, using the inbuilt GPU on the NUC. So the same system can do early season, it can do late season, it can do curve, and these are all validation sets. So none of these are used in training when we train the neural network on the robot, and you can deal with lots of occlusions and all kinds of things. So that was very cool. And the next thing that we've been doing, working with Vikram Adve, Sarita, and Shasha, and their students, Yifan and Hashim, is trying to get that exact system from an Intel NUC to like a Raspberry Pi 4. So, applying neural network approximations so that we can bring that cost of this robot down. So the NUC is maybe like $800. A Pi 4 is maybe, like $50, $60, or even like if we can bring it to a Jetson Nano, and it'd be good. So not only can we do that, it seems like with deep learning and these approximations, but we can also increase the speed at which the robot drives compared to the LiDAR. So while the LiDAR was at max, could drive at about a mile or a mile and a half an hour, these vision-based robots can drive 3 miles, 3.5 miles, and basically they could go faster, of course. It gets quite tricky with the bumpiness in the field faster than that. So last thing before we switch into the questions is manipulation. So of course, all of these robots are just going around. Maybe they can do things like planting cover crops and maybe mechanical weeding. But in order to really kind of come towards these polycultures, we need these robots to do something more. They need to harvest. They need to prune. They need to do all kinds of things that humans do. So ag equipment today is kind of here, right? So it can be really large scale, but it doesn't have a lot of dexterity. People are here. They're small scale but they're very dexterous. Our robots are not good at anything right now, either of those things. We need to bring them here. So there's been a lot of interesting work going on in this area. So this is work with Girish Krishnan at the university with soft arms. And these soft arms are kind of inspired by octopus arms and elephant trunks. And here's our RSS last year's paper where we have this hybrid arm. So we have the arm, the hard part of the arm, and then this trunk thing comes out. So when the berry is on the periphery, you can just use the rigid arm to pick the berry. But when the berry is inside, then this thing can extend and go in there. So there's still a lot of work to be done here. So right now, this is all in what we call task space control. So the location of the berry is known to the robot, and then it's using reinforcement learning to get there. What we're working on now is kind of like the adding the perception and doing all of that. So towards all of this, we have the Illinois Autonomous Farm that we've created at the University of Illinois. Microsoft has been very generous, donating lots of equipment and some time for us. EarthSense has donated some robots, and it's located on the ABE facility. And this is part also of the AI Farms National AI Institute that I'm an associate director on. Vikram Adve is the director of that, and that we launched last year with funding from USDA through NSF. And these are all the wonderful people that are now working on this, and this has gone like way beyond just my group at this point. There's a lot of different people that are looking at many different aspects of these things. So here's some of them who have been working with the robots on the autonomous farm. So that's kind of all I had for the formal talk bit, and I just want to kind of close on some of these. If I think IoT in ag, what are some of the things that come to my mind? So first and foremost, of course, edge AI, right? It has to be on site. There is no cloud anywhere like 5 miles from where I am in Champaign. Cloud doesn't exist, right? I mean, there's maybe some connectivity, 2G, 5G is like a dream away. And then we need to create like, interesting networking solutions. There's cellular, there's LoRa, there's FarmBeats, there's all these kinds of different things that we need in order to even just move data around on the farm itself. And then there's lots of unknown issues here, I think that we have to look into. So there's the attenuation issue. So the crops are basically 70% water. So getting signals through that is hard. But on the other hand, there's a lot of energy available on the farms, in terms of solar and wind that can be harnessed. So that's kind of where I'd like to stop.